Okay, good afternoon, everyone, and welcome to the post-lunch session. In this session, we have two speakers with us, Philippe Corboz and Andre SrCu2. Each of them will give the usual 40-minute talk. The first talk is by Philippe Corboz. You can start now, Philippe.
Okay, thank you very much. And also let me thank once more the organizers for giving me the opportunity to speak here. And my apologies again that I didn't manage to, I was not able to join in person. And I really hope there will be another opportunity to come to Bangalore. So in my talk, I would like to tell you about recent progress in understanding the physics of strontium copper borate, which is effectively described by the Shastry-Sutherland model. And I will focus here mostly on results obtained with IPEPS, which is a two-dimensional tensor network ansatz, right? So I introduced it already in the tutorial yesterday, and we also heard about it in Frederic's talk this morning. So I will keep the part on the method very short here. So I would like to tell you about 4 different projects. 3 of them are in collaboration with experimental groups. So the first project is on strontium copper borate under pressure at finite temperature, where we revealed a critical point at finite temperature analogous to the critical point of water. Now we have heard about this already in Frederic's talk this morning, so there's going to be a partial overlap, but I would like to repeat some of the main ideas here and then also show you some additional IPEPS results here. So this was in collaboration with the groups of Henrik Rönnow and Christian Rueg, with Frederic Mila, and then several more people on the theory side, Andreas Honecker, Bruce Normand, Stefan Wessel, Lukas Weber, Andreas Leuchli, and then also my student, Schelto Krone. Okay, and then part 2 will be about SCBO under extreme conditions of both field and pressure. So that's together with the group of Sarah Haravifard at the Duke University. And here I will tell you about our discovery of a new type of 1/5 plateau and new supersolid phases in this extended pH phase diagram. Okay, and then in part 3, I will tell you about a project which is going to appear soon on the archive on SCBO up to the saturation magnetic field. So that's also with Frederic, and then Toshihiro Nomura from ISSP in the group of Yoshimitsu Kohoma, and then also the groups of Sergei Zerlitsin and Yuji Matsuda and Hiroshi Kageyama. So here we found a close agreement between IPEPS and experiments, and also we got some new insights into the behavior of the ultrasound velocity. And in the very end, I would like to tell you about an ongoing work where we study the Shastry-Sutherland model with interlayer coupling using a new IPEPS approach for layered systems. Okay, now let me start with an introduction to the Shastry-Sutherland model. So I've already briefly heard about it this morning. So it can be seen as a spin 1/2 Heisenberg model on this particular lattice, so with some additional couplings here on the diagonal. Or alternatively, you can also draw it here as a lattice of coupled dimers. So where J denotes the coupling strength on the dimer and J prime the inter-dimer coupling strength. Okay, so this is an interesting lattice. And now what's interesting is that this system is described in the real material in strontium copper borate, which is a layered material where the copper 2+ ions, they carry the spin 1/2, and they form the same lattice as you can see here in the middle. Now let's have a look at the phase diagram of this model as a function of J prime over J. So for small values, the ground state is given by an exact product of singlets along the diagonals, so that's a dimer phase. If you go to the other limit, you recover the square lattice Heisenberg model, so we have a nil phase. And then in between, there have been several predictions for intermediate phases in the past. And several years back, we confirmed that this intermediate phase is a placket phase, so a non-magnetic phase, which breaks translational symmetry and forms strong correlations around these plackets here. Now, this might not be the end of the story. So very recently, there has been some new calculations where they suggest that there could actually be a very narrow quantum spin liquid in between these two phases. So this might still not be fully settled, but I will not go into the details of these new calculations. Now, strontium copper borate lies in the dimer phase, but close to the transition into the placket phase. And what's now one of the most fascinating features of this material is its very rich behavior once you put it in a magnetic field. So early on, several magnetization plateaus have been found in experiments. And on the theory side, the challenge was to try to understand what magnetic structures are realized in these magnetization plateaus. Okay, so early on, it was clear that this system has almost localized triplet excitations, right? So if we take the ground state here given by a product of singlets, we can just promote some of these singlets to triplets, which are going to align with the external magnetic field. And then one can also easily show that if you put two triplets next to each other, that on the mean field level, they're going to repel each other. And this has led to the natural common assumption that these magnetization plateaus correspond to crystals of these triplets. Okay, so here are some early suggestions how these crystals could look like for the 1/8, 1/4, and 1/3 plateau. So the triplets here in red and the singlets in black. So you get these crystals. So that was back in 2000. And then after that, there have been many more experimental works where new plateaus have been revealed. And then also many theory works trying to understand and predict the structure of these triplet crystals. However, it turned out then that for the low-lying plateaus below the 1/4 plateau, that the picture of these triplet crystals is actually not correct. So in 2014, we could show with IPEP simulations that these plateaus here correspond not to crystals of triplets, but to crystals of triplet bound states. So these objects here are SZ=2 objects. So these can be seen as bound states of two triplet excitations. And it's these objects here which then form crystals here in these magnetization plateaus. So while we have this picture below the 1/4 plateau, above the 1/4 plateau, we still have the picture of triplet crystals. So here I show you the spin structure for the 1/4, 1/2, and 1/3. So essentially you see here these diagonal arrays of triplets in these crystals here. So these spin structures are taken from this paper here, which was also a joint work with experiments where we did fits to the experimental magnetization curve using different approaches to extract here the relevant coupling 0.63. Okay, so this is strontium copper borate in a magnetic field. I will come back to this later in my talk. And now another very interesting possibility of this compound is to put it under pressure, which effectively changes this ratio J prime over J. So we can really drive it from the dimer phase into the placket phase or even into the nil phase. And this was achieved already in a series of experiments here, in particular in these experiments by Guo et al., where they performed specific heat measurements. So here you see this characteristic peak they obtained in the gapped dimer phase. And here you see the position, the peak position here is given here by this purple line here. So that's the maximum of the specific heat peak. And what they found is that this maximum is pushed to lower temperatures as a function of pressure. It reaches a minimum here, and then it goes up again. And where it reaches a minimum, there's another small feature appearing here, which they assign to the transition into the placket phase. Right, so this was back in 2020, and at the same time, there was also specific heat data in Henrik Renoff's group, which showed very similar behavior. So again, you have the specific heat peak, which goes from high temperatures, so from these temperatures to lower temperatures, reaches a minimum here, and then goes up again. And what you can also nicely see here is that the specific heat peak becomes very sharp here. Now, it was actually thanks to Frederic, so he had the right intuition what's actually happening here, namely that this feature here corresponds to a critical point at finite temperature, as we already heard also in this talk this morning. So the situation is that for the ground state, we have a strong first-order phase transition between this dimer phase and the placket phase, and this first-order transition extends as a finite first-order line to finite temperature and then terminates here in this critical point. And this is really very reminiscent of the critical point that you can find in the phase diagram of water. So here you have liquid water and here water vapor. And if you cross this line, so that's a first-order line, which goes up here and terminates here in this critical point. Okay, so this was Frédéric's suggestion. And then the question was then, can we reproduce this feature also using IPEP simulations of the Shastry-Sutherland model in this regime? Now, the physics here was inspired also from another model. So in the fully frustrated bilayer model, which also shows a critical point at finite temperature, which was what's discovered from quantum Monte Carlo simulations. We also heard about this in Frédéric's talk, so I will skip the details here. And now very briefly, a few comments on the methods. So I explained this in detail yesterday in the tutorial, but for those who were not here, so we consider an IPEPS, which is a two-dimensional tensor network ansatz to represent a wave function in the thermodynamic limit. And it consists of a unit cell of tensor, which is repeated on the lattice. And by using different unit cell sizes, we can target different states with different magnetic structures, for example, right? So that's the ansatz we use here. And then the accuracy of the ansatz is controlled by the bond dimension of the tensors. And then for the finite temperature calculations, I explained this also yesterday. So instead of representing a wave function, we can also represent a thermal density operator. So now we have an ansatz, with an ingoing and outgoing physical leg on each side. And what we do in practice is to use a bilayer ansatz. So we use this for rho at half of beta, and then combine this with its complex conjugate to get the thermal density operator at beta, which has the advantage that this is Hermitian by construction. So equivalently, one can see this also as a purification of the thermal state, which is really equivalent here. So it's a bit of a matter of taste if you want to see this as a, as an operator or as a wave function with an ancilla side here. Okay, so now let's get back to these results. So this is experiments, and let me show you now here the IPEPS results obtained from the Shastry-Sutherland model, and you can nicely see here that we obtain here a very similar behavior with a strong peak down here, so reminiscent or indicating the presence of a critical point. So we also studied the effect of the finite bond dimension. So by extrapolating in the bond dimension and then by converting also to real units, we found an estimate for a critical temperature around 3 Kelvin, which is in good agreement with the temperature of this peak found in experiments. Then let me comment also on this white region down here. So essentially here, nothing happens anymore because the ground state is sort of trivial. But we had some numerical issues here, which are mostly due to the fact that the ground state is indeed trivial. So that's rather a numerical artifact here. And we were able to get rid of this artifact by adding small Dzielodziński-Maria interactions, so which make the ground state slightly entangled. And these interactions are also known to be present in strontium copper borate. And you see in this case here, we got rid of this feature here. And what we can also see here is that the physics of the critical point does not really change when we add the DM interactions. So we got further insights here also from computing the correlation length, which can be computed from IPEPS. And you see that it peaks at the same location as the specific heat peak. Now, it's interesting to see that the divergence region here is extremely narrow. So if you really want to see the diverging correlation length, you have to zoom in a lot here to really see this divergence. But overall, we find here really a clear evidence of a diverging correlation length compatible with a critical point. Then we also computed the spin-spin correlation on a dimer, which you can see here jumps from a dimer phase which is -3/4 for the singlet, to a value close to 0 in the placket phase, right? So you see here clear evidence of this first order phase transition when you jump over this line, and it terminates here at the critical point. Now, the simplest model which reproduces the same behavior is just a 2D classical Ising model in a field, right? So if we first take H equals to 0, then if we come from high temperature here, we reach the critical point of the 2D classical Ising model here, and below we have spontaneous symmetry breaking, so ending up in either -1 or +1. And now if you can cross this phase diagram also horizontally, and then you encounter down here a first order phase transition where the value jumps from a negative value to a positive value. And the magnitude of the jump is simply equal to twice the magnitude of the order parameter, right? So we can use the jump size as a measure of the order parameter. So this is what we did here. And then we can perform a scaling analysis of the order parameter around the critical point to extract the value of the critical exponent beta. And what we found here is a value which is compatible with the the expected value of the 2D Ising universality class, right? So giving strong evidence that we have here a critical point of the 2D universality class. Okay, so overall, we can really say that we managed to identify this critical point here doing the IPEP simulations, and that was for the first time. So we also heard in Frédéric's talk about the fact that quantum Monte Carlo has a very hard time in doing simulations here due to the negative sign problem. So that's a very nice result, but there's also open challenges. So for example, we were not able to really systematically study the phase transition into the placket phase because the simulations get increasingly challenging as we go to lower temperatures. And so this was still out of reach, but we hope that we can get there then in future with improved methods. Another challenge is that actually there's still a discrepancy regarding the nature of the placket phase. So in theory or in experiments, neutron scattering experiments suggested that the placket phase is such that the plackets are formed around plackets including a dimer, which we call a full placket phase. Whereas in theory, we have this empty placket phase, so with plackets containing no dimer. Okay. However, it turns out that these two states are very close in energy. So we investigated this systematically in this paper here, where we considered an extended Shastry-Sutherland model, so with two sets of inter and intra-dimer couplings. And then we performed computations of the phase diagram along several cuts, and we could find that already a small deformation of the standard Shastry-Sutherland model leads to stabilization of this full placket state, right? So this full placket state is really close by in parameter space, but in the end, the precise couplings are still not known yet. So please remember this full placket phase because it will play a role also in my next part of my talk. Okay. So here, I just wanted, before moving to the next part of my talk, I just wanted to quickly advertise this work here, related work together with Piotr Czarnik, Marek Rams, and Jacek Czermaga, where, so that's another example of a finite temperature IPEP study where we managed to determine the phase transition temperature into the 1/2 plateau here by performing IPEP simulations and performing a systematic scaling analysis. So in this case, we obtained an estimate for the critical temperature of about 3.5 Kelvin. Okay, so just to show you that now it's in principle really possible to also probe the finite temperature properties at finite magnetic field. But now we will move to ground state calculations, and let me go to the second part of my talk. So here we consider strontium copper borate under both extreme conditions of field and pressure. And in Sarah Haravifart's group, they performed experiments using the tunnel diode oscillator technique. So essentially what they do is to put the sample into a detection coil, which together with a capacitor forms an LC circuit. And then if there's a change in magnetization, this will have an influence on the resonance frequency F here of this LC circuit. Okay, or more precisely, the change in the frequency is proportional to minus the second derivative of the magnetization. So whenever there's a non-zero value, it implies a slope change in the magnetization. So whenever you encounter a phase transition, for example, with a jump in the magnetization or with a strong change in the slope, this can then be observed as an anomaly with which you can then detect the phase boundaries. Right, so here you see the experimental data, so as a function of field, and the curves correspond to different pressures, so they have been offset by a constant here. And the arrows show the identification of these anomalies. Now, if you look at these two arrows here, you can see that the location of the anomalies are pushed to lower fields as pressures increased. And then beyond 1.9 gigapascal, there's a qualitative change in the distribution of these anomalies, so indicating that we have entered the placket phase here. Now, on the IPEP side, our goal was to compute the phase diagram and to identify these anomalies with the phase boundaries. Okay, so here I show you the result for the phase diagram. So it's both combined theory and experiment. So the black symbols show you the location of the experimental anomalies, and everything in color is IPEP's data. So let's first focus on the high field region. So here you see the 1/4 plateau, and which agrees well here with these two anomalies, right? So with the phase boundary of the 1/4 plateau. And also these two anomalies found here are in close agreement with the phase transition into the 1/3 plateau. So below the 1/3 plateau, we have an extended 1/3 supersolid phase, so with the spin structure shown here. And then we also have a large region here of the intermediate plateau. So these are the bound state crystals. So there's many of them which are also pretty narrow. So we just combined them here in one blue region. And now the most interesting new feature in this phase diagram is the appearance of this 1/5 plateau, which came a bit as a surprise, and then also this new supersolid in a 10x2 unit cell. So what's the nature of these new phases? So here is the 1/5 plateau. So we can see that it has a vertical stripe structure, right? So there are vertical stripes which are separated by boundaries made of spin singlets, so along this red dashed line here. And then in the middle of the stripes, we find strong triplets, and in between, there's a weaker pair of triplets. So this is neither a crystal of triplets nor a crystal of bound states, but it's another type of plateau here. Now, how can we understand this state? Now, what we can also see is that there's actually a strong formation of plackets here, which are full plackets, right? So remember, I mentioned this full placket state before, which was one of the competing states at zero field, but it's higher in energy than the empty placket. So it's interesting to see that this type of physics, this type of correlations appears here in the ground state at finite magnetic field. And now, having this state in mind, we can also obtain an understanding of the structure of this state. So in the full placket phase, you have triplets on the dimers within the plackets and predominantly singlets between the plackets. And these triplets here form effective spin 1 Haldane chains, so in horizontal direction. So the full placket phase is actually equivalent to a Haldane phase. So with this picture in mind, the way to think about this state is to see it as a spin 1 diamond chain at the magnetization plateau of 2/3, right? So the ground state here is well understood. So you have just an aligned triplet here on these sides. And then on these sides, you have an anti-symmetric linear combination of a magnetized side and a non-magnetic side, which in the end then adds up to 2/3, or this unit cell here would then correspond to a magnetization of 1/5. Okay, so this is the cartoon picture which somehow describes the structure of this state here. And let me also mention that a similar state was found in a Shastry-Sutherland tube made of two orthogonal dimer chains, so in this paper here. Okay, and now the supersolid phase can be understood in a similar way, so it can be seen as a descendant of this 1/5 plateau state. So you can obtain it by taking the 1/5 plateau state and then rotating the spins by 90 degrees, either clockwise or anti-clockwise. And then there's also then a finite component in the direction of the magnetic field, and also here along this line of the domain wall here. Okay, so in the end, it's interesting. We found these two type of states, and these two type of states can be described using the physics of the full plaquette state, which is a higher energy state at zero magnetic field. Okay, now let me move to the third part of my talk, so this in the end is first of all an extremely remarkable achievement on the experimental side, because they managed for the first time to reach the saturation field of the sample. So by going to fields up to 150 Tesla, and they performed both the ultrasound velocity measurements and the magnetostriction, from which they identified new anomalies, in particular also the saturation field at 139 Tesla. And then on the IPEP side, our goal was again to see if we can understand the appearance of these anomalies. And then another point was to try to get some insights into the strong decrease of the ultrasound velocity that you can see here appearing in the 1/2 plateau. Okay, so here I show you the IPEP's phase diagram. So here between the 1/2 plateau and a fully saturated sample. So it's dominated by this 1/3 supersolid phase, so the green area here, so which can also be found at lower fields above the 1/3 plateau. And we found two different types of 1/3 supersolid phases, so with slightly different spin structures shown here. If you go to higher fields, there's a transition into a period 14 supersolid phase, so with the structure shown here. And then right before saturation, there's a strong competition of different competing states, so including also this period 8 supersolid, which is stabilized at larger values of J prime over J. And then finally, we reach saturation. There's also a tiny narrow period 10 supersolid phase here in between these two phases. Now let's focus on a cut at 0.63, so the relevant value for strontium hyperborate. And let's now compare with the experimental anomalies. So this anomaly here can be naturally assigned with the end of the 1/2 plateau, so it's in a good agreement. And also the saturation field is in good agreement between theory and experiments. And then this anomaly here could be naturally assigned to the phase transition between the 1/3 supersolid and the period 14 supersolid phase. Okay, so overall, we found very good agreement for these three anomalies. This anomaly here is a bit more tricky because it appears at lower fields, and this transition here is quite subtle, so it's not clear if that would actually be seen in experiments. So it could be that this anomaly here corresponds to another phase transition into another phase, which is maybe not captured by the simple Shastry-Sutherland model, but which would require additional interactions. So that's still an open question here. Okay, and then we also got insights into the reduction of the ultrasound velocity. So what you see here is the relative change of the ultrasound velocity as a function of field. And we focus here on this C66 acoustic mode, which comes with a strain pattern as shown here. So where the deformation is such that it comes with opposite signs on horizontal and vertical dimers. And what you can observe is that there's really a very strong reduction in the 1/2 plateau, whereas in the 1/3 plateau, there's essentially no reduction. Now, one can show that both the first and second derivative of the magnetic energy contribute to the elastic constant. So that's a result which was shown by Frederic. So essentially what you need to do is to write out the total energy, so consisting of the magnetic energy and the structural potential energy, and then expand it to second order. And the elastic constant is just given by the second derivative of the total energy. And then it turns out that both these terms here intervene as linear terms and contribute to the elastic constant. And so hence also to the change in the ultrasound velocity. And now it turns out that already the first derivative explains qualitatively this difference, because if you compute it with IPEPs, it has a large magnitude in the 1/2, but it's vanishing from the 1/3 plateau. And the reason is the following. So the 1/2 plateau has a checkerboard structure. So it has large positive energy on the vertical dimers and negative energy on the singlets here. And now if we compute the derivative, and the derivative is taken with respect to this strain pattern here, meaning we take opposite signs for the two couplings if we vary them. And this leads to two contribution, which adds up, which leads to a large magnitude. And this is in contrast to the 1/3 plateau, which has an odd periodicity. So it has triplets on both the vertical and horizontal dimers, which leads to a cancellation of terms when you compute the derivative such that it gets 0. Okay, so already the first derivative can qualitatively explain this difference here. And then we also included the second derivative, and from performing a linear fit to the experimental values of the change in elastic constant, we could then obtain an IPEPS estimate for the change in sound velocity. And you see here, the values we obtain are actually in remarkable agreement with experiments. Okay, so again, this work is still not published, but it should appear very soon on the archive. Now, let me move to the second part of to the last part of my talk, which is about the Shastry-Sutherland model with interlayer coupling. So we have seen that the standard Shastry-Sutherland model is really very successful in describing many of the features of strontium copper borate. So not only qualitatively, but to a large extent also quantitatively. But of course, there's still limitations. So particularly on the quantitative level, there are some mismatches. And one example is the extent of the placket phase, right? So if you look at the extent of the placket phase predicted from experiments, then it turns out to be considerably smaller than the extent predicted from theory, right? So if we take here the data by Guo et al., they find a transition between 2.5 gigapascal and 3 gigapascal. And if you convert this to J prime over J, we have a value here, which is much smaller than the theory value. And the main reason for this discrepancy is the lack of interlayer coupling, which we don't include in the 2D model. And this was already discussed in an old paper by Koga back in 2000, so where he considered the 3D model, so with a small J double prime between the 2D layers, and then used Sears expansion to compute the phase diagram. And you can clearly see that the placket phase, it becomes increasingly narrow as you increase the value of J double prime, right? So the antiferromagnetic phase becomes favored over the placket phase with increasing J double prime. And the reason is simple, because you can take the antiferromagnetic state and stack the layers on top of each other without frustrating the antiferromagnetic order. So which means the J double prime will lower the total energy. And that's in contrast to the placket state, where the interlayer coupling has only little effect on the energy, right? So this naturally shifts the balance towards the antiferromagnetic state. Now, there have been different values predicted for J double prime, so values around 0.09 to 0.29 from fits to magnetic susceptibility. And then this value here was predicted from some ab initio calculations, but overall, there's still no consensus here what the value could be. Now, we recently started to reinvestigate this problem using a new IPEPS approach for layered systems. So this was developed by my student, Patrick Flahr. So the idea is that we start from a 3D tensor network ansatz with anisotropic bond dimensions. So with a larger bond dimension for the interplane direction, for the intraplane direction, and then a small bond dimension between the planes. So if you take dz equals to 1, this just corresponds to a product of IPEPs of different layers. Now, the main challenge of 3D tensor networks is the contraction of the network, right? So if you do a full 3D contraction, this is computationally very expensive. So here we came up with an approach which explicitly exploits the anisotropic nature of the state. So let's first discuss, so if you take dc equals 1, then this would be simple because then we only have individual layers that we can just perform standard 2D contractions. And now for larger DC1, what we do is the following. So imagine if you want to compute a local expectation value in the middle of the system.
Philippe,
what we do,
you just have about 5 minutes just to keep an eye on time. Yeah.
Yes, I will try to wrap up soon. Yeah. So imagine you want to compute something here in the middle. So what we do is to first effectively decouple the layers away from the middle. So by projecting this here to dz equals to 1. And then we can contract these layers using standard 2D tensor network approaches, so surrounding the center sites. And then in the end, we can just contract then the remaining tensor network. Right, so this has the advantage that we can recycle standard 2D tensor network approaches for the contraction, but we can still take into account the dominant interlayer correlations by the connections that we keep here in the center. Right, so here we kept one connection, but you can also keep several connections in the center. Right, so we call this the layered corner transfer matrix method. So we benchmarked this approach for the anisotropic 3D Heisenberg model, where we found a close agreement with the quantum Monte Carlo results. So here, this is for dz equals 1 as a function of 1 over the intraplane bond dimension. So already, a product of IPEPs planes already gives quite a good result. And then you see here, when going from dz1 to dz2, we can actually quite considerably improve that result. And then we also found that this is an agreement if we would do a full 3D contraction, which is computationally more expensive. Okay, and then we started to apply this to the Shastry-Sutherland model. So here's the current phase diagram where we see that, so essentially for dxy equals to 6, we see that the phase boundary does not change much anymore. So we are close to convergence here. And then we can also consider the transition value from experiments, which would suggest that we are around here, so that the interlayer coupling is estimated to be around 0.03. Right, so this is one application example of this new layered IPEPs approach, and we believe that this is also going to be a useful tool for future studies of layer systems. Okay, so with this, I would like to summarize. So we have seen that strontium copper borate under pressure and in the magnetic field exhibits very rich physics. So we have found a finite temperature is in critical point. We have revealed new plateau and supersolid phases at high pressure and field. We have found results up to saturation in agreement with experiments, and also new understanding for the reduction of the ultrasound velocity in 1/2 plateau. And then we also got some new results for the Shastry-Sutherland model with interlayer coupling. Then on the method side, I have shown you that IPEPs is a versatile tool, not only for ground state, but also finite temperature calculations. And I told you about this extension to layered systems. So with this, I would like to thank all my collaborators, so in particular Frédéric Mila, for many years of fruitful collaborations on this compounded model. And then in the end, I would like to thank you for your attention.
For this very exciting talk. Thank you. Few questions, any from the audience or from the online participants?
Sir, can topology and symmetry, hello, can you hear me?
Yes.
Topology and symmetry of mathematics branch can be explored using PPS?
I didn't quite understand your question. Could you please repeat it?
Topological phases of matter and symmetry properties of a material can be explored using PPS?
You mean PEP? Yeah. So in the end, there's PEPs offers actually a natural framework to classify and explore topological systems with topological order. So different types of topological order will be reflected by different symmetries, which are encoded in PEPs, right? So here we did not make use of that, but there's several groups working along these directions to classify topological ordered systems by classifying by according to the symmetries that these tensors obey. So that's it offers actually quite a nice and a natural framework to study topological order.
Thank you.
Thanks. Any other question?
Well, maybe I can ask one question,
Yes,
Philippe,
please.
About the last part of the talk where I'm not involved. It's very nice that you can include interlayer coupling. There are two issues about the plaquette phase. The first one that you mentioned here is the width. It seems to be smaller than what was expected if there was no interlayer coupling, but there is also the nature of the plaquette phase. And we were wondering at some point, I remember, if the full plaquette phase could maybe be stabilized by interlayer coupling. Do you have any thing to say about this?
Yeah, so indeed, we actually looked into this, but it turns out that the interlayer coupling really has very little effect on these, 2D states. So both the empty plaquette and full plaquette phase, the interlayer coupling has very little effect, changes the energy only very slightly, so that the difference in energy cannot be overcome, right? So the interlayer coupling does not really help to shift the balance towards this full plaquette phase. So that's what we observed here, yeah.
Okay, thank you.
Question? Well, Philippe, I have one quick question. That a plaquette phase generally is the one without what you call empty plaquette phase. Numerically, that is what was suggested earlier. But you see experiments seem to suggest the full plaquette phase or the one with a singlet bond in between. So is there any understanding on that, why it so happens?
Well, I mean, what we have seen from the, from the work we did, the work I mentioned here, we have seen, that these two phases are really very close in parameter space, right? So the plain Shastry-Sutherland model really gives rise to this type of plaquette phase, but we know if we start slightly deforming the structure, so if we add, if we modify the model, then this phase here is not really far away. So from that point of view, it could be that in order to capture this, we would need, to consider a modified model to reproduce this full plaquette phase.
Or if you think that interlayer coupling may have a role to play or no role to play, I don't know.
Yeah, so indeed, so that was an interesting question that also Frederic was asking, but indeed, so we did not find that the interlayer coupling would have a significant effect on this competition here. Yeah.
Thank you very much. So let us thank the speaker once again. And